So the next section is about some exceptions to the octet rule. We've talked about this a little bit. There are a few elements you want to be aware of. So the octet rule is our main rule that we use to help us draw Lewis structures. We want to keep in mind a few of these exceptions because they do play in situations where usually where formal charge is involved. So for beryllium, when we look at where it is, it's in the second column of the periodic table. So normally the elements in that column, magnesium, calcium, etc., don't share electrons. Because once we get to magnesium and calcium, like if you think about magnesium, it exists with a 2+ charge, right? Because losing its 2 valence electrons gives it 10, the same number as neon, and since it only has 12 protons, that's not too much of an imbalance. The ratio there is kind of close to 1. But for beryllium, with only 4 protons, if I lose 2 of them and I only have 2 electrons, which would be the same number as helium, the nearest noble gas, that's a 2-to-1 ratio. That's too much of an imbalance. So for atoms that don't create too much of an imbalance in terms of the ratio, they will often exist as ions, and that's true for most metals. Even though beryllium is a metal, it forms covalent bonds rather than forming an ion most of the time because it would create a lot of imbalance. So to avoid that imbalance, it will usually just form 2 bonds. So if it forms 2 bonds, like with 2 hydrogens as it's shown there, does that give it a noble gas configuration? No, I've got 4 valence electrons. Which element is that similar to? Carbon, right? Carbon has 4 valence electrons if it's not bonded to anything. That's not a noble gas. So beryllium with 4 valence electrons is not making a noble gas configuration. That's what makes it an exception to the octet rule. Why does it do that? Well, because being in 2A, in group 2A, its formal charge would be 2 minus the number assigned. And if we have 2 bonds, that's 0 lone pairs, and half of the 4 shared, that's 2 minus 2, that's 0. So here is a case where the formal charge is preempting the noble gas configuration, which is usually the opposite of how it is. Usually it's more important to make a noble gas configuration than to have a balanced formal charge. But in this case, to make a noble gas configuration would create too much formal charge. So instead of doing that, it just balances its charge out usually by forming 2 bonds. If we look at boron, the next element over, we have a similar situation. So if we think about boron, look at boron, it needs 3 electrons assigned to it to keep its charge balanced. So what boron will do will usually be to have 3 bonds, which puts 6 valence electrons around it. That's not the same as a noble gas. So if the boron has 3 bonds, it is an exception to the octet rule, or an exception to the idea that the noble gas configuration is the main thing that determines the stability of an atom. Boron is pretty stable with only 3 bonds, because if with 3 bonds, it could be bonded to hydrogen or whatever. With 3 bonds, its formal charge is going to be 3 minus half of the 6 shared around it. There's 0 lone pairs, so that's 0 in balance. Boron can, however, form a noble gas configuration sometimes. So with only 3 bonds, it still does have, in the second energy level, more space for more electrons. So something comes around with a pair of electrons that's maybe creating too much negative, it could come in and start sharing with the boron. So if I think about a water that might be missing a hydrogen, which would be a hydroxide or OH minus, that oxygen creates a negative formal charge. That needs a positive charge to balance it out. So just because the boron's nucleus has space in the second energy level to hold more electrons, those could come in there, and I could create a structure that would create a 4th bond on a boron. If it did that, what would the charge be on the boron? Yeah, it'd be -1, because now it would be 3 minus half of the 8 shared electrons, which would be 3 minus 4 or negative 1. So what's more stable? To have a little bit of an imbalance in charge on a small atom, or to have a balanced charge and not have a noble gas configuration? It really depends on the situation. So you want to also be aware that for boron, it's a little bit flexible. If I bring in something that is unstable, that had a negative to begin with, then we'll probably start sharing. At least that makes a noble gas configuration, right? Because in this case, what we said was the BH3 that we started with was exposed to an OH minus. The OH minus already has an imbalance in charge. So if I already have a negative to begin with, is it more stable to keep the negative on the oxygen, or is it more stable to complete the noble gas configuration for the boron and have a negative? Probably more stable to complete the noble gas configuration in that case. But if I don't have anything around that's creating a lot of negative charge or any extra electrons, the boron is also fairly stable without a noble gas configuration. I can't really make the same argument for carbon. So we want to recognize boron's flexibility. Carbon, though, is not nearly as flexible. If I put carbon in the same situation, if I break carbon's noble gas configuration by putting only 6 electrons around it, what will its charge be? That would make a positive, because carbon has 4 valence electrons. It needs 4 to be balanced, and I'm only assigning 3. So with a positive charge, now it's really pretty unstable, because it has an empty space to bring in more electrons, a full positive to attract them. It's going to be much more stable if I can make 4 full bonds around the carbon. So we don't really see carbon breaking the octet rule nearly as much as boron does. Other exceptions to the noble gas configuration or octet rule is the situation where you have an odd total number of valence electrons. Not very common, because if I count up my number of valence electrons and I find out it's an odd number, there's no way to put them in pairs. And if I can't put them all in pairs, there's no way to complete the noble gas configurations for all the atoms. And so that creates something called a free radical. It's kind of a cool name. Free radical is simply an atom or molecule that has an unpaired electron. And it's going to be unstable, right? Because this nitrogen here needs another electron to complete its noble gas configuration. So we'll start reacting with things and pulling electrons off them, and undergoing reactions with, depending on the molecules. If those are molecules in your body that's reacting with, it could cause some undesired effects. So you want to be aware of that. If for some reason you see something with an odd number of valence electrons, it's not going to have a noble gas configuration. But it probably won't be a very stable structure. And then the third category of exceptions to the octet rule are including most of the non-metals. So sulfur, phosphorus, chlorine, even silicon, the elements that are non-metals in row 3 and below can all hold more than 8 valence electrons, and sometimes will. So here's an example where we have a sulfur that has 12 valence electrons instead of 8. Is that okay? Yeah, it's okay, because sulfur's valence level is the 3rd energy level. The 2nd energy level only has space for 8 electrons. The 3rd energy level has the 3s, the 3p, and the 3d, and so it has space to hold more valence electrons. Even though the 3d orbitals are farther out, when electrons are in there, they're not nearly as stable as they are in the 3p. There's not a huge difference there. So if I think about sulfur with only 4 bonds, making a noble gas configuration to whatever I connect with it, that sulfur is going to have a 2+ formal charge. Not going to be that stable. And so if I have additional atoms that have negative charges, like these fluoride, they'll just come in here and start forming more bonds, because the space around the sulfur's nucleus is in the 3rd energy level. It's not that far away from the sulfur's nucleus. It's not a huge amount of shielding. And I've got too many negative charges in one area, so they just come in there and share, and that balances out the formal charges. If I have enough fluorines around the sulfur, I can balance out its formal charge. So for elements in the 3rd row and below, you may see them with the noble gas configuration, but you may not. And if they have more than 8 valence electrons, it will usually be because that's the number that balances out their formal charge. So formal charge is pretty important. All right, so let's look at this example here. So the Bi3, if I were to draw a Lewis structure, I would come up with this, right? I put the boron in the center. Its electronegativity is like 2.1. Actually, I think it's 2.0. And the iodine is like 2.6, I think. So the boron is less electronegative for sure. I put it in the center, connect the iodine, count up all the valence electrons, add them around the more electronegative atom first. Then I realize the boron doesn't have enough valence electrons. So what should I do? Well, I should recognize that boron is sometimes an exception. So as we said, the boron can accept more, but then that creates a formal charge, but at least then it makes a noble gas configuration. So those two factors are kind of offsetting. If the noble gas configuration dominates, then my structures would look like this, where I would see that they would have complete noble gas configuration around the boron. But then, because that creates a formal charge, I might say, well, maybe that's not as stable. Because with a formal charge on the boron, that's an area of imbalance, and it might be better if I didn't have that formal charge. In this particular case, it also creates a formal charge on the iodine. Whichever iodine is sharing extra electrons will end up with a positive. So probably the best structure might be the one without the extra double bond. Right? So we see that with the boron having only 6 valence electrons is okay, it's relatively stable. But these aren't hugely unstable because it does complete the noble gas configuration of the boron, so what we have here is resonance. All 4 of these structures are different resonance contributors. And so when I have resonance between structures that are kind of similar in stability, what really should exist then is the average of all 4 of them. And to show that, I would recognize that between the boron and each iodine, there's a single bond plus between the boron and each iodine. I have additional electrons moving around due to the electron's ability to shift in and out. And so that means that the boron will have a partial negative and the iodines will have a partial positive as a result of the fact that on average the iodines have a situation where there's no charge and a situation where there is a charge, so the average situation is only a partial charge. Let's look at one more example here, ClO2. So between chlorine, which is 3.0, and oxygen, which is 3.5, I want the chlorine in the center. I want to connect the 2 oxygens to that. I want to count up my valence electrons. Chlorine brings in 7, it's in 7A. The oxygen brings in 6, and I've got 2 of those. So that gives me a total of 19. Okay, I've got an odd number of valence electrons. This means it's going to be a free radical. I'm not going to be able to put them all in pairs. So what should I do in this situation? Still follow the same steps we did before. So I've used up 4 so far, so I've got 15 left. I want to put them around the more electronegative atom first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I have a free radical, I don't want that probably to be on a highly electronegative atom, right? A free radical is a space where I don't have a full pair of electrons. So if that's going to happen, an atom is not going to have the full number of electrons it would normally have. It's probably not going to happen on a highly electronegative atom that attracts electrons well naturally. So I've got 4 more. I've got 3 more. I want to put them on the central atom. So I'm still following the steps for drawing Lewis structures in the same way. So I've used up all my electrons. Now I want to try to do the best I can to make as many noble gas configurations as possible and also keep in mind the formal charge. So right now I've got noble gas configurations, Ng, noble gas configurations around both oxygens, but I don't have enough electrons around the chlorine to make its noble gas. I can't make its noble gas because I have an odd number of electrons. So should I share some of these electrons in to make a double bond or not?
Yes.
Well, just based on the noble gas configuration, it's not going to make much of a difference. If I do, either way, the chlorine is not going to have 8 valence electrons. It's either going to have 2, 4, 6, 7 or 2, 4, 6, 8, 9. So it's better for chlorine to have 7 valence electrons or 9. Doesn't really make much of a difference. Either way, it's not a noble gas configuration. It is a third row element, so it is possible that it could have more than 8. It could have 9. So to distinguish between them and figure out which is better, what should I look to? Formal charge. So if I calculate the formal charge on this one, let's look at this chlorine up here. Formal charge on the chlorine on the top molecule is going to be 7 minus the number assigned, which is the 3 lone pair electrons plus half of the 4 shared electrons. So that's 7 minus 5. That's a plus 2. Ooh, that's kind of a lot of formal charge in one area. That's probably not ideal to have 2 full formal negatives and 1 formal plus 2. Once I share a pair from one of the oxygens, though, then I only have 1 negative and 1 positive. Can I also think about sharing a pair from both sides? Yeah, now if I look at the chlorine, it's going to be 7 minus the number assigned, which is the 3 lone pairs plus half of the 8 shared. That's 7 minus 7. So this has 0 formal charge. So probably the bottom structure looks like the best structure to me. Either way, I'm not going to make a noble gas configuration for the chlorine. Either way, I have a noble gas configuration for all the oxygens in all my structures. So if the noble gas configuration is not really different from one structure to the next, what I look for is the difference in formal charge. But because oxygen is more electronegative, it might pull these electrons to some extent, so I might see these other ones as resonance contributors. The difference between them is that they're in resonance. So maybe the actual structure looks mostly like this one, but this might not be a full double bond because the resonance contribution might make like a little bit less than a full double bond.